It's great. So let's get started, everyone. So hope you're enjoying the last day of spring before summer comes tomorrow. So today we're going to talk about projection onto a basis. Again, this is something you maybe, hopefully, probably have seen a bit of in a linear algebra course. We reviewed a bit of it earlier in the semester, but it's going to be important for setting the stage for dimensionality reduction. Just looking at the schedule, we are kind of really switching topics. We kind of had a long kind of stretch where we were talking about linear regression into moving into gradient descent as a way to solve linear regression. And this gave us a supervised problem where we had a bunch of these explanatory variables, and then we had one label, a dependent variable that we were trying to predict. So we were trying to learn a function mapping from one onto the other. This allowed us to use cross-validation to see how well things were working. And using cross-validation kind of allows you to kind of smooth over a bunch of the modeling steps and kind of not worry about the modeling as long as it under cross-validation seems to work well, then you can kind of trust it. We're moving into unsupervised learning where we do not have a special column that is the label we're trying to predict. And so the game's going to change. We no longer can rely on cross-validation. We're going to have to rely on, well, kind of modeling and geometry, and you'll just kind of have to trust that this is the right way to model the problem. These problems, dimensionality reduction and clustering, are to some extent interesting in their own right, but they are most powerful when used inside of other parts of analysis as kind of substeps within them. So we'll mostly motivate them as kind of things are interesting on their own, but where they typically will show up, as you'll see if you continue on in things in data science and AI, is kind of inside of other algorithms. These come up as critical ways of taking something really messy and compressing it to something that you can do more kind of learning and understanding. Okay, so we'll talk about projection on basis today. This will mostly be setting up what is the problem, what is dimensionality reduction, try and give you some conceptual understanding of it. We'll be thinking about high dimensional stuff, which will be a little bit kind of harder to picture and to think about, but I'll try and reduce it down to 2 or 3 dimensional pictures that are capturing the insights of what we're doing. We're going to be talking about linear dimensionality reduction. So we're not doing weird sort of nonlinear stuff in this class. That's mostly, I don't trust most of the nonlinear stuff most of the time. So that's one reason we're not doing it. It's also more sort of complicated. So most of what you want to do for dimensional reduction is the linear stuff we will be doing. And we'll be talking about stuff based on principal component analysis as kind of the central approach, which we'll get to in the 4th lecture of this. And that is kind of really the core behind probably 90% of linear dimensionality reduction. At a very, very large scale, you may be doing something else, but we won't get into those in this class. So, okay, so that's kind of what we'll be doing the next 4 lectures here. The other thing to mention, homework 4 is due soon. That was posted before break. Unfortunately, posted the link to the wrong data sets before. So if you had downloaded the data sets right before break and didn't see the email, you could probably download the new ones. They were the wrong size. That was the most clear sort of giveaway that they were the wrong data sets. It looked like when I posted them, only 2 people had turned in the assignment at that point. So hopefully not too much of also an issue, but just be aware that I posted the wrong data sets that did match the dimensions. If you haven't started on this yet, this one is, I would say, the most programming heavy assignment of the semester in this course. Some of the other ones may be kind of conceptually a bit trickier, but if you're less familiar with programming in Python, especially part 2 goes a bit beyond the examples, more beyond the examples in the class than most of the other programming that we'll be doing. So don't wait until the very last minute to do those. Also mention for homework 1, I will, how many people have played with function 2 so far? Okay, it's function 2 is kind of weird. This is intentional. It's not easy necessarily to find the minimum of function 2 to satisfy the requirements for the homework. You just need to run gradient descent and say, okay, here's what happens when I ran it. But I would like you to try and do better and use some of the other techniques. And for those who do significantly better than kind of the typical student, I'll give you some bonus points. Yeah. Yeah, so you can't do batch versus stochastic really for F2, right? You need a decomposable function to do batch versus stochastic. That's what you get and you construct in number 2, in question 2 here. Okay, but yes, so play around with the learning rate. That's a good place to start. Or things beyond choosing a fixed learning rate, right? Those are the sort of things, and those are going to be trickier going beyond the examples of code we give in class, but that's kind of what you need to do when you're kind of not in a very nice situation like you are in F1. F1 is a very, very nice situation. Actually, question number 2 will set something up that will be nice in the same way F1 is nice. Okay, but if you're doing something like deep learning or something like that with a non-convex situation, you may encounter things like F2. It won't be exactly like this. This is the 2-dimensional function, but it's hopefully gives you something fun to play with so you can see beyond just just running it directly. Okay, great. So make sure you get working on that. There's some TA hours and stuff if you need help, and you can ask you can ask questions on so Canvas if you get stuck. Okay. So today we're starting on dimensionality reduction. And so what kind of is so essentially what this means is we're going to have kind of data where each data point is in RD, and D is very big, let's say equals so let's say 1,000. Okay, so we're in a very high dimensional vector, and we want to map to kind of X prime, which is going to be in RK, where K is small. And small might mean 2 or 3 or like 10. So we want to map to a much smaller dimensional vector where this is X, this is X prime, right? And so we want to think of our data as like a really small vector with lots of coordinates in it, right? We have X1, X2, up dot, XD. And now X prime is, say, X prime 1, X prime 2, maybe x prime 3. So I just have 3 coordinates in it. Right, so I'd like to do this for all of my data at once. So, I've captured maybe a lot of information, x1 to d, but the goal of this is to go down and represent it, and not just one data point, but a whole bunch of data points at once into this lower dimensional space. So I want to start with thinking of why would I want to do this? Why would I want to map a very high dimensional vector down to a much lower dimensional vector? So what do you think?
The two things that I thought, first off, a lot easier to work with low dimensional vectors anyway. Second, in a very high dimensional vector, it's very probable that a lot of that data doesn't apply to what we're looking at anyway. So we always care about all 1,000 points when we only need.
Yeah, great. So these are good points. So when you say much easier to work with, what do you mean by that?
What do you mean? Visualize.
Okay.
For at least for me, in my mind, it's a lot easier to think of how I can manipulate it rather than having to think about how to manipulate it 1,000.
Yeah, great. So if we go down to k is equal to 2, or maybe k equals equal to 3, we can plot the data, right? And this is really cool. Helps us understand it, right? One of the other things you said, which is also great, is that there's maybe unneeded info in so RD. So so maybe we could even say that so it may be even like overfit, right? So if we could think of one way we got high dimensional vectors was we took the original data and we did this polynomial expansion up to a really high degree polynomial. Maybe those degrees of the polynomial we got is how we got this high dimensional vector. We're actually giving us too much control over what we could fit the data over. So maybe we're overfitting it, right? So in fact, there are some statistical arguments that if you are in really high dimensions, you going down properly to a low dimensional subspace and making a prediction on there might generalize better to new data. This can sometimes be true, right? Do you have something else you wanted to add to it, or that was it? Yeah. So one other way it could be that it's easier to work with, other than you can visualize this data because you can plot it, is that it might also be computationally easier. So just to read one data point takes so O of D time. So if I'm in like so if I'm in like 10 dimensions, okay, 10 dimensions isn't so bad to read. If I'm in 1,000, it starts to be a little bit painful. If I have lots of data points in 1,000 dimensions, this can take an extra factor 1,000 to read the data set than if I was in only 2 dimensions. Okay, if I'm in 1,000,000 dimensions, which is not that uncommon, or 1,000,000,000 dimensions, this sort of thing can happen now. Just reading one data point takes a long time to do it. Okay, so if we could somehow reduce the data to a lower dimension, then just the fact of reading it into my algorithm takes much less time. Okay, there's also something called the curse of dimensionality. So how many people have heard of the curse of dimensionality, maybe? All right, so this is what can happen when when there are some algorithms where where the runtime is something like O of n to the d. So it might be if you're doing this in 1 dimension or 2 dimensions or 3, it's reasonable to do with a reasonable size data set. But as you go to 1,000 dimensions, if you have like even 2 data points, or 10 data points, or 100 of them, it's like 100 to the power 1,000 runtime of the algorithm. This just becomes infeasible to run. Okay, so some algorithms, there are a number of algorithm techniques that grow exponentially with the dimension. And so if I wanted to run those algorithms in a high dimensional setting, it's just not possible to do.
What's the word after?
So runtime. So I ran a little bit out of room there. Runtime. Okay.
And also what is the word over what after RD?
Unneeded info in RD and maybe like overfit. Maybe. I'm hesitant. The word overfit, I think, is kind of, yeah, I put in scare quotes because the notion of overfitting, like I mentioned, this phenomena of like double descent, maybe says this is not true. Maybe we don't actually overfit in these high dimensional spaces. Yeah, but you could think of it, maybe there's information that you don't need in this high dimensional space. And I think that's a valid way of thinking about it. And there are some statistical arguments that there's some real data in a subspace, and then the rest is just like observational noise. One place this high dimensional data has come recently has been in these learned representations, right? A lot of the way that we represent language is by these individual words, or actually these tokens, which are sometimes sub-words, but for most common words, and probably the most 10,000 common words in English language, it's taking the whole words, and each word you embed in a very high dimensional space. Okay, so this became popular with these word vector embeddings about 10 years ago, maybe a little bit more, 10 to 15 years ago. And then there were these extensions, which were not at one location for a word, but more complicated representation, is the basis for like ChatGPT and all these language models. And these all work by embedding language, individual words in these basically individual words or kind of strings of text into these high dimensional spaces. And so you can try and say, well, what if I ran dimensionality reduction on this? Like the typical spaces now are roughly 4,000 dimensions, like 4,096 is the most common thing I've seen for like these language models. And what if you reduce the dimension of these? Well, you retain some of the information, but the performance of the algorithms almost always goes down if you directly apply dimensionality reduction on these and just say, I'm going to represent in some lower dimensional space. You see, why would I need these extra dimensions? They seem to have information I don't need. But if you do dimensional reduction, you lose some sort of information. All right, so that's not to say they're useless. One of the most important methods for doing kind of for taking a language model and adapting it to a particular setting. So it's called fine tuning. There's a method. So there's a method called LoRa, low rank kind of way of doing fine tuning, and it basically uses dimensionality reduction inside of this algorithm. It doesn't destroy all the information, but it uses dimensionality reduction and techniques like we'll describe inside of it to make this process more efficient. Okay, so we'll see kind of some aspects of this. It's very important to visualize data, to plot it down to low dimensions. Sometimes there's information unneeded. Sometimes it's just to speed things up. And so you get some computational advantage by doing dimensional reduction. Okay, so there's a variety of some needs for doing this, and it shows up in useful inside of many other algorithms and places. All right, so let me go back and describe what sort of data are we talking about. Okay, so again, we're talking about input. We'll say A is going to be our data, and we'll think of this as a set of these n data points. Each is in our D, right? And so again, D is going to be too big. And so, but we we typically, we are going to have n larger than D. So for what we'll talk about in this class, well, in the motivating it for what we'll talk about, we'll think of n as still larger than D and D is too big. Okay, so maybe D is 1,000 and n is like 1,000,000. Okay, so that's kind of a place to think about, right? And so then we can draw this as a picture for A. You can think of it as going to be a matrix, right? Where I'm going to have D columns, and we're going to have n of these rows. Okay, so n rows and D columns, and then I will have one of these. This is going to be AI. This will be one of the data points, and so this data point will live in RD. Right, so this will be one data point, and I'm just going to stack them. This dimensional reduction is going to use the language of linear algebra, right? So we'll think of our data as vectors, and they're going to live in a matrix. And this we'll think of our input as this matrix. To do dimensionality reduction, we're not going to want to just apply this on one data point, but all the data points. And to tell us what is the right way to do it is something that's going to work well collectively across all of the data points. Okay, think of this kind of like our training data here. We want it to work well in the whole training data set. All right, and so again, that means we can think of this AI as this vector AI1, AI2, and up to AID. And so this is kind of clunky. There are two subscripts here, right? So this would be, this one object here would be AIJ, right? There's one element in this big matrix. All right. So what I want to stress on this slide is some kind of examples where this arises. Kind of these, one would be these word vector. Okay, and so the old school way of doing this, which is easier to think about, so I'll mention this now, would be things like called word, so word to vac. And what this will do is it would typically have each AI in R equals 300 dimensional space. And how do I get the representation of this word in this 300 dimensional space? I kind of learn what that should be. I try and want words that appear in very similar context and language to have very similar vectors. And I kind of read a bunch of text and I say, well, these sentences, there's a bunch of very similar sentences that had cat in them and also had dog in them in the same spot. And I could have replaced cat and dog and the sentence still would have made sense in either of them. So the vectors for cat and dog should be very close to each other. And so it learns this representation. Okay, so so kind of what is a little bit more tangible of what this could mean is I could think of having, and these word vector embeddings, usually they have for about the top 100,000 words in English. Okay, there are word vector embeddings for all sorts of other languages. And for maybe the top 100 or so languages, these work reasonably well. And for English, usually the top 100,000 words. Maybe if you go past 300,000 words, they start to become so weird. It's just like emojis and stuff like that, and like misspellings of people's names. But usually the top 10,000 words is really enough for conversing. I probably, the whole semester won't use more than 10,000 different words in this class. And 100,000 is still a huge vocabulary. Okay. Something more tangible, let's say I have N, so weather stations. Okay, so there's a research group that I've collaborated with here at the U that monitors weather from 40,000 plus weather stations across the US. And they're streaming data to it's collected and cleaned here in the atmospheric science department. And you could think of that these are sending in reports of the temperature and other things every hour, right? So it's, you could think of, but let's say I have now D days of the kind of the max temperature. Okay, so I have 40,000 weather stations, right? So now I might have N equals 40,000, and D might equal to be like 100 days of the max temperature. Okay, so I could think of this, and now I want to understand something about how to the structure of how weather stations are similar to each other, but I don't need 100 days. I should be able to capture that with fewer than 100 days. Okay. Another example of this that's kind of so common. Let's say I have N so N days of kind of a stock price. Okay, and this would just be one stock. So I'm going to look at the stock of like Amazon. So I'm looking at the price of Amazon. Okay, and so this will give me some data set of N. So this was on day 1, day 2, up to day N equals, it's like 10,000. Has Amazon existed for 10,000? I'm not sure. Let's say that if not Amazon, think of like GE or one of these older companies. Let's say I have 10,000 days of stock prices. And how do I'm going to turn this, so let me actually call this uppercase N days. And I want to turn this into an N by D matrix. And what I'm going to do is I want to set a window of D days. Okay, so it'll look something like this. So like, let's say D is equal to, let's say 20 in this case. So I have 20 days. And I'm going to say this is equal to 1 data point. This is going to be data point AI here. Okay, so this, I'll take a set of 20 days, and this will be data point AI. And then I want to look at the next window of days. So this will be now, it's going to have some overlap. This window is AI plus 1. Okay, so I'm going to take consecutive days that are kind of shingled on top of each other. And each kind of consecutive set of D days would be 1 row in this matrix. Right, so now this was AI, and this was AI plus 1. Okay, so there's going to be, there's some weird correlation here that this data point, these are equal, right? So if I have some offset of 1, this value here and this value here has to be equal, but that's fine. Okay, so this is often modeled. This is often modeled for like some regression problems where I'm trying to predict what is the value of the stock going to be on the next day. Okay, so I can actually store whatever value comes next and put this as like a label data in some other column. Okay, so I can use this to try and make a prediction of how the stock's going to change. did it, you know, all these day traders do, okay, it does this down and then down again. Now I think it's going to go back up, and you can try and learn these patterns. I think it's kind of mumbo jumbo, but also there's billion-dollar companies, so based on this like micro trading or these kind of these, so these high-speed trading algorithms. When I was in grad school, there was a researcher I worked with, one of the famous national labs, and so he said, you know what, I'm going to give up this career and go into kind of this high-speed trading. And we all thought he was crazy. He was going into day trading and stuff, and he made a lot of money doing this sort of stuff, getting it early on. I think trying to look for patterns on your own faster than these high-speed traders who are plugging it in is maybe not realistic, but you can find certain patterns in these stuff prices. Okay, and what I want to kind of give from these examples, what I think is the most important thing from these examples is that all of these cases have each, it's the most important thing. I better not write it off the screen, right? Okay. In all of these examples, in all examples, each coordinate has the same units and meaning. All right, so all the coordinates, each coordinate has the same units and the same meaning, right? If we go back to this with the weather station, every day is recording a max temperature. It's measuring in Fahrenheit, not Celsius, or maybe it's Celsius, not Fahrenheit, but it's consistent across all of them. In this example, everything is the price of the stuff. Okay, the units of this haven't changed. Okay, so I can directly compare these against each other. In the word vector embeddings, it's a little bit harder to see. They don't really have meanings by themselves, but they're learned in some way so that the distance makes sense and the individual coordinates can be directly compared against each other. Okay, and so for all the data we want to do dimensionality reduction, we need to have this property. Okay, so if this property is not true, then do not apply dimensionality reduction. All right, so if we do not have that all the units, all the coordinates mean the same thing, we should not be applying the techniques we're going to be learning here. Okay, there are some sort of fancier ways to try and do this. If you take the data mining course, you will learn about some ways to try and get around this. They're more complicated. You need some additional information. You need some sort of supervision. So you need some labels on something in order to tell you how to do dimensionality reduction. But if we don't have it and they're mixed units, we should not be applying these techniques. There are a number of textbooks out there that will show examples of applying dimensionality reduction techniques with data sets with mixed units, and it's just nonsense. Okay, it does not make any sense. You could change the units and you change the answer you get. Okay, so this is really important, and I've kind of chosen a bunch of examples here, and there are more in the book that says here are examples where this makes sense to do. There are other examples from like movie recommendations where there are a bunch of users and every user rates a bunch of movies. Okay, or there was some other example is you are, yeah, so you're trying to kind of So take a picture of like the Utah teapot. So how many people know what the Utah teapot is? All right, so it's this famous kind of actual teapot. If you go to the front office, you can see one of a small number of replicas of this original teapot. That was one of the first 3D models ever built. That a lot of computer graphics was kind of developed here at the University of Utah in the 1960s. And so what they did is they put a bunch of like coordinates on it, and they developed a bunch of different techniques to build meshes and stuff on top of the teapot. A more modern way of doing it would be to put that teapot on kind of some scanning device and shoot a bunch of lasers at it and see where those lasers bounce back to and how far away it is. And you measure a distance in a bunch of points, and then you rotate the teapot. Okay, and you're getting, let's say, 10,000 values of the depth, and all you're doing is you're rotating the teapot. That rotation is 1 degree of freedom, right? But you're getting these 10,000 dimensional vectors. Okay, so that 1 degree of freedom of the rotation of the teapot should tell you everything you need to know about the rotation of the teapot. That's the only free parameter here, but you have 10,000 coordinates at every point in the rotation. So I shouldn't need those 10,000 coordinates. I should only need one value, the angle of rotation. So this kind of makes sense as a dimensionality reduction problem. Okay, so these are kind of where we would want to try and use this. All right. So let's get any question about this, and we'll get into mathematics of like, what does it mean to do dimensionality reduction? Okay, but this is an important point. Okay, I hope if you take a course from me, you will not make this mistake. Yeah. Great.
But if you think that in the two-dimensional situation, such as the weather situation, then how come so my question will be like, how come you changing one vector, one value that gonna affect the whole system?
Yeah. So the weather stations, I may not make sense to go down to one, just one dimension. And what is the right dimension I should go down to? This is a good question, and I won't be able to give you a magical answer that will always give you the right number here. But one thing you can imagine is these are weather stations are, for the most part, they put some on top of buses, but if you ignore those, they are fixed in one location. Okay, so that means there should be a 2D coordinate, maybe 3 because they're on the Earth and the Earth is curved, but a 2D coordinate that describes where the weather station is. That may not be what you find because all you're getting is the temperature value, but there's probably some two-dimensional correlation that's strong about where they are. So that's probably a good starting point. And then there might also be some other effects that has to do with, say, the elevation or what sort of climate it's in. You can imagine a small dimensional space that captures all the information in. Okay, and so like if you can find that space, that would be much easier to work with than a 100 or a 1,000 dimensional space. Okay, yeah. It's not always clear what the right dimension is you should go down to, and sometimes it makes sense, and sometimes it's kind of, there's not a clear answer. Great, that's a great and really important question. Okay, so how and what is dimensionality reduction? We're going to go through this. We're going to start drawing on what we know from linear algebra, okay? And we're going to think about two objects, a data point, right, which was AI, and this was a vector in RD. And this was what we would like to do the dimensionality reduction onto. And we're also going to have a unit vector, which is also going to be a vector v, and it's also going to be an RD. Because it's a unit vector, I know that the norm of the unit vector is going to be 1. Okay. That's the property I have. And a projection is going to be, again, my favorite operator. Is going to be the dot product between AI and V, right? And so it'll be useful to draw a picture here to remind you what's going on. We're going to have a point V, right? And because it's a unit vector, that means that it's going to kind of live on this unit ball. Okay, that's not going to be so important. What is going to be important is that we could think of it as this vector from the origin, and then we're going to imagine this line that is a continuation. Okay. And then we're going to have our data point is also going to live somewhere in RD, right? So I'm only able to draw things in 2D, but everything should make sense in RD as well. Okay. And what we're going to do is, what is this dot product doing? It is going to be a projection operator. Okay. We're going to do this pi of V of AI, which is going to be the projection of A onto the closest point on this line. Okay, so this is going to be the closest point on the line through the vector V to the input point AI, right? So I'm finding the closest point on that line to the point A. Okay, so I'd like to do this projection operator. Okay, think of this as I'm taking the data point and I'm projecting it onto this line is a one-dimensional space. Right, so I'm going to map it to the closest point on the one-dimensional space. That's this point here. This point is pi of V of AI is this point here. Okay, and the nice thing is that this is, we can derive what this point is using the dot product. Okay, so I can get that in particular, this distance from the origin, the length along this vector to that point, that length is going to be exactly AI dot V. This is true because it's that length of that distance of the projection is the dot product because it's a unit vector. Okay, so the fact that V is a unit vector means that the dot product is measuring the length. Okay, but so that doesn't tell me what this object is. Is this a scalar value? Is this a length? What is this projection?
It should be just, it's not a scalar value. It is basically another point in our view.
Great. Yep. So this is also a point. So I need to get this point back. So I need to somehow recover this point. This is a d-dimensional point that I know is this far away. This gives me a scalar value, the dot product. It's this far away in this direction. Well, that's going to be exactly equal to, it's this far away, AI dot V, and then it's in the direction of the unit vector V. So this is a scalar, the green part is a scalar, V is a vector. It's a d-dimensional coordinate. It doesn't have any length information. Its length is 1, right? So now I'm going, this tells me length of 1, this tells me how far to scale it. Maybe I'm scaling it by like 1.2. So I take this vector in this direction, and this could be a d-dimensional vector, so I could be high-dimensional space. And it tells me how far to move along this direction, and that directly encodes this. Okay, so this dot product right? This, the dot product here. And remember, this is just the sum over j equals 1 up to d of aij times vj, right? So it's just the sum of all those coordinates. So it's a very simple operation to do. And it's gonna, and if I have this vector d, then this tells me how to project it onto this vector. This is doing dimensionality. So now it's a little weird. This is the key operation in dimensionality reduction, but I'm getting back a vector that's d dimensions again. So I started with A, which is the vector A1, AI, that's a vector that's d dimensions, and I get back a vector that's d dimensions. Okay, so maybe this hasn't helped very much yet, right? I could apply this to a different point here, AI prime, and also project it here, right? I can also do the projection onto here. And this gives me a different, again, AI prime is a d-dimensional vector, and its projection is also a d-dimension. Okay? So this, it seems like it might kind of be helping. They're both living on the blue line now. So I need to get, how do I get a lower dimensional representation? Well, if I just look at how far they are from the origin on the blue line, that gives me a one-dimensional value. That is, again, just the dot product. The dot product gives me a one-dimensional value. It's a scalar. Maybe I do just want the scalar. In fact, the scalar gives me a one-dimensional parameter. And so I can take two data points and both give them a one-dimensional thing. And I say AI prime is now somehow smaller than AI because it's got a smaller value. Now I can compare them in one dimension. Okay. Typically don't want to go down to just one dimension, but this is kind of the start of the idea. I want to go down to k dimensions. Okay, and this, how I go to k dimensions, this will be the building block, but let's go and think about how do I do a projection onto k dimensions. Yes.
So think about why we are multiplying the after the top of dot of theta.
I'm describing, again, this is I of v of ai, and this is going to be a vector in RD. Remember that these are both vectors in RD. So it's a two-dimensional picture. So think of a two-dimensional vector. This is a data point. This is the x coordinate. This is the y coordinate of this yellow, orange, whatever color this is, of this data point. It's a two-dimensional. So this is a one-dimensional value. This is a vector value. The scalar times the vector gives me back a d-dimensional. Okay? So I told you how to get the projection, but I also said I also want, maybe I just want the scalar. Okay? And these things are kind of mixed up right now. We'll go through, and in some cases you want the vector, sometimes you want the scalar. So we will, in some cases, want both of these. But before we get into that, let's go to multi-dimensional projection setting, and then we'll think about this a bit more. Great, great. Very good. Then that was a good question. I'm sure other people, could use the refresher as well. All right. Okay, so now we want to talk about a subspace. I'm going to call this B. And so a subspace B, and I'm going to represent this by a set of basis vectors. And we're going to call this V sub B, okay, to describe this. And it's going to be a set of V1, V2 up to VK. Okay, so they're going to be k-dimensional vectors, and each of these will be an element of Rd. Okay, so each Vj is going to be element of Rd. Okay, and so this value k here, this will be the low dimension k, right? That we're going to project down to a low dimension k. To do that, I need v of these basis vectors. And I'm going to assume my subspace, assume this contains the the origin, right? So the all zeros vector. Okay, so I'm going to define a basis so that I assume the subspace contains the origin. This will be kind of, will make stuff a lot easier, and we will get rid of this next week. Okay, but the basis needs to have it's going to have two requirements, and then it will give me one property. Okay, so I'm going to assume, again, for these vectors, for these Vj, right? For these Vj, I'm going to have these 3 points. I'm going to have that the norm of each Vj is going to be equal to 1, right? So these are all going to be unit vectors. So unit vectors. And I'm going to have that Vj dot Vj prime, the dot product is going to be 0 if j not equal to j prime. Okay, so if they, for two different vectors, their dot product will be 0, that's going to make them to be orthogonal. So these are orthogonal. Okay, so I want them to be unit vectors. I want them to be orthogonal. And then, okay, so what this property is going to mean is that I will be able to say that for any point x in B, okay, I will be able to write, I can write x is equal to j is equal to 1 up to k of some alpha j Vj, where this guy is going to be a scalar here. All right, so I'm going to be, for any point that lies in this subspace that contains the origin, if it's defined by these basis vectors that are unit vectors and they're going to be orthogonal to each other, I'm going, and I don't need orthogonality, I just need linear independence, but orthogonality will be nice. We will be able to get it. Then I'll be able to write this x as a kind of a linear combination of the basis vectors. So this gives me a way to write any point in the subspace. That's what this means. And so I'll be able to do this if I have these basis vectors. And so that means that I can now define a projection onto B as the projection onto B. I used to define this pi of V for one vector. Now I'm projecting onto the basis A, onto the basis B, which is defined by a set of k of these vectors. I'll be able to write this as the sum of j equals 1 up to k times the projection onto Vj of A. So I can project onto each of the individual basis vectors and just add these vectors up. the output of this, remember this output of it was a vector, and I can just do vector addition. Okay. In fact, this will be, and so if you understand the projection operation, then just geometrically, you can think of it that way. I can also write out exactly what this was. This was Vj dot A dot Vj. So I can also write it in this form, right? And in fact, if you remember, this is also going to be a scalar. Okay, and so what does that mean? It means that if A was X, it was in the basis, then I'll be able to recover it exactly in this way. So this is just another way of recovering. I can get back X if it's in the basis. There's a way to write it with these scalars. In fact, these scalars allow me to do it. If X lives in the basis, then I'm able to kind of the projection, the closest point, right? So remember, this gives me the closest point on B to input A, right? So if I take this input point A, I want to find the closest point on the subspace to it, and I can do it by just applying these dot products on each of the basis vectors, assuming I have a basis vector for the subspace. Okay. So hopefully, if you understood this picture with one dimension, I'm just doing. Now I say I have k of these vectors, and they happen to be. They're already unit vectors. They happen to be orthogonal. I just apply to each of these, and I add these vectors up. That's all the projection is. Let me draw a picture now, but hopefully the mathematics is not too kind of like bewildering now, because we built up from the one-dimensional version. Okay, so let's draw a picture of this now. I'm going to draw a picture in R3. Try to. Okay, and where I'm only have a two-dimensional surface here, but we'll try and draw this onto R3. Pretend we're in 3 dimensions. Okay, and we're gonna have 2 vectors, V1 and an orthogonal vector that's also a unit vector. We'll call this one V2, right? So I have these 2 vectors, they're orthogonal and they're unit vectors here. And so these will give some basis for a subspace here, right? So I can kind of think of there being this 2-dimensional subspace that kind of lives in here. So these are not necessarily sitting on a 2-dimensional plane, but they're 2 vectors kind of coming out, and there's a subspace in 2-dimensional piece of paper, right? So there's a 2-dimensional piece of paper. It goes through the origin. And it's defined by these 2 basis vectors along the edges of the piece of paper. Now, it actually fills out to infinity in these other directions as well, in addition to the green one I've shown. But if I just color that in, everything's going to be green, right? So that's not going to. But think of it as this paper coming out of the screen, and the sides of the paper are defined by V1 and V2. They're orthogonal to each other. If I look at the 2-dimensional subspace of the paper, they form this nice right angle here, right? And if I make them the same length, they're going to be unit vectors. Okay, so that's kind of what we're picturing here. That's our subspace we're working with. So that means that we're going to have a for B is this object, and the 2 vectors are V1 and V2, right? Okay, so that's the situation we're in. And now we want our data point A. We'll just say it's A here, and this is, okay, our piece of paper was here, and A is sitting somewhere up in space. So I want to project it down onto this plane here. So I want to find the closest point onto the plane, and it will look something maybe like this. This point here, we'll call this is projection of B of A onto the space. Okay, so that circle red point now lives in this green plane that's in three-dimensional space. Okay, and I promise you that this is somehow this is a right angle projection onto here. Okay, so you should be kind of visualizing that. Okay, and now we can think of the coordinates. The coordinates onto this space here. Okay. Okay, so I'm going to write this. How do I describe this? I need to describe it using the basis, right? And so we can describe it based on this point here. This will be pi of V1 of A, and this will be pi of V2 of A. And that would be if I projected it directly onto here, or directly onto here, this would be a right angle. Remember, it's a little bit it's projecting down onto these 2 points if I project them onto these lines through here. And then to recover pi of B of A, I just add those two vectors together, right? There's a vector here and a vector here. That's the sum of those two vectors with respect to this origin. Okay. They're both vectors in three-dimensional space, and so that red circle is also a vector in three-dimensional space. Okay, I can also think of them. Okay, so what's useful though is I can also think of these as I can measure this length here. This length is V1A, and this length here, this will be V2A, right? These are the lengths of these two along these subspaces V1 and V2. Okay. And so what's powerful is that this is now a point that lives in R3, but I can also write this point as a coordinate of at a two-dimensional coordinate, V1A, comma, V2A. Okay, so this I can think of as now living in R2. Okay, so now I can think of this point either as living as the projected point in the full three-dimensional space by adding the vectors together, or I can now say, well, maybe I want to live in this plane, right? This piece of paper plane, and the piece of paper, the plane is only 2 dimensions. So now I want to give it 2-dimensional coordinates. And those 2-dimensional coordinates are precisely just the 2 dot products. Okay, so I can either think of this projection as giving me, okay, it's a point that lives in 3D, but it happens to live on this plane. It's one of those nice points where that equation works out. Or I can represent it by just the 2 coordinates in this plane. The same way that when I did the 1-dimensional dot product, I got the 1 coordinate of the length. Okay, but now I'm in 2-dimensional space. So I can get 2 coordinates, the 2 dot products of the orthogonal bases. So now I have reduced it down to 2 dimensions. Okay, so now I've kind of gone from RD, which is D was equal to 3, down to R2, where K is equal to 2, right? So now we think of this was equal to D, and 2 was equal to my K. I've gone from 3 down to 2. Okay, but the same sort of framework works from 1,000 dimensions down to 10 dimensions. If I have 10 orthogonal vectors in 1,000-dimensional space, I project onto each of them. I get the dot product that tells me that coordinate, and I do it 10 times. I get 10 coordinates, a 10-dimensional space. And I do this for each of the data points. Okay, so there are kind of two outcomes here, kind of two outcomes of projection. Okay, I have pi of B of A, which lives in RD, but on this subspace B. Or I'm going to get this V1 dot A, V2 dot A dot VK dot A, and this is going to live in RK. Okay, so I can either get a d-dimensional point, but it happens to live in the basis, or I can get a k-dimensional point that's described in some parameter space of this basis. Okay, so I kind of have a new coordinate system here. So these new bases give me a new coordinate system, the same way that I had 3 coordinate systems here before by these 3 black kind of vectors. These were kind of boring vectors, right? We would call this one E1, which was 1, 0, 0. This one E2, which is 0, 1, 0. And this one E3, which is 0, 0, 1. And if I did a dot product onto these with A onto these 3 vectors, this is a valid basis. I would get back the original coordinates. Okay, so you can check it out. If I dot onto the E1, I just get back the first coordinate because I multiply the first coordinate by 1 and the second and third coordinate by 0. Right? So this checks out. I'm just doing it with a different coordinate system here. And so if I choose the right coordinate system, then I project onto it. This is linear dimensionality reduction. Okay. So this is telling us the mechanism of linear dimensionality reduction. The question is, so I've told you the algorithm to do the dimensionality reduction, but I haven't told you how to choose the basis B and its basis vectors V1 up to VK, right? Well, and we will not get to the algorithm until Wednesday, but let me tell you what I want those vectors to do. Well, what would the objective be? What is the goal? So there's how to choose, but then what is the goal here in the choice of these basis vectors? I want to choose K basis vectors, and we'll later on try and give you guidance on how to choose the value of K. Okay, but let's say I told you I want K basis vectors, and they have to be unit vectors and they have to be orthogonal. How do I choose them? What do I want them to do? And so you could think of like a picture now where I want to choose kind of V1 and V2, and I have there's some subspace in here, and this lies in some high dimensional space. Okay, and there's going to be now a bunch of these data points. A1 that can project onto here. A2, which maybe is below and projects up. Right, and all of these, and I'm going to have a whole bunch of these data points, and I want to project them onto the subspace. So I'm going to be given, remember, my input is going to be A, which is going to be this matrix A1, A2 up to AN, right? So this is in N by D. I'm going to give an input of a set of N vectors, each in D-dimensional space, and I want a projection that is probably good for all of them in some way. What does good mean? What do I want with the projection? If I do dimensionality reduction, well, if I have to project them very far, if this length is very long, that seems not as good as if the length was short. A short projection is probably better. I have a better representation of the original vector if I don't have to move it very far. Okay, so I want these lengths to be small. So again, we're going to define the residual Ri is going to be AI minus the projection onto B of AI. Okay, and okay, this gives me a vector, and I don't want to worry about is it I of B of AI minus AI or AI minus I of B. What order does it matter? So I want to, the residual, usually I look at the length of this. Okay, this is the length. Remember, this is the 2 norm. And so that tells me this would be this length here. This is R3, right? This length here is R4. Okay, and so I guess I want those lengths to be small. I want to find the subspace for a large number of vectors that is close to all of them. Okay, so how do I combine this together into a single goal, a single kind of cost function? We're going to go back to our old friend, sum of squared errors. And so our cost of BA is going to be the sum over I equals 1 to N times AI minus pi of B AI squared. So I want to minimize, I want to find the subspace that gives me, minimizes the sum of the squared so residuals. Why do we do the sum of the squared residuals? Well, who can guess? Why do we do the sum? Okay, yeah, so there, some could be negative, this projects down, this projects up. In fact, well, they're vectors, so some of the coordinates are negative, but so I somehow need to do a length. So I could have done it without the square here. I could have just done the sum of the residuals. So already taking the length avoids the issue of the negative. So why do you think I square them? Why did we use sum of squared errors before? Okay, maybe you remember you like the statistics lectures at the beginning and you're like, this is probably a maximum likelihood estimator of something. Maybe there was probably, you assume it came from a low dimensional subspace with normal noise or Gaussian noise in some other dimensions. And we took a log likelihood of that. And when you took and we assumed they were independent. So when you took the independent, it was a product of Gaussians. And when you took the log of that, it became a sum of squares that we want to minimize. That might be a reason why you would get sum of squared errors. This is a valid way to think about this. It's going to minimize some likelihood, assuming that the data came from a low dimensional subspace with Gaussian noise. Gaussian is high dimensional normal distribution. That's one way to derive it. And so if you have normal or high dimensional Gaussian noise, then this is the optimal model. Okay, this is an okay way that's kind of retrofitted onto here. What was another reason that we liked the sum of squared errors before? For instance, in the one-dimensional case where we could take the mean of the data, or we are doing regression. And then in regression, we had this cool algorithm we could apply, right? Where we had a closed form solution for the answer here. Right? We could do this matrix inverse. Remember this equation? Like the X transpose X inverse times X transpose X Y gave us the optimal parameters for sum of squared errors. Are we going to have a closed form solution here? There's not a closed form solution. After you take this class, it'll probably be closed form for you because that's built into every software package you will ever use the rest of your life. But it's not actually closed form as directly as that. As directly as taking the mean. Do you think we'll be able to run gradient descent on this? And it'll be a nice, strongly convex function because the cost function we're minimizing over the coordinates of these v's is going to come from a quadratic equation. Will we be able to run gradient descent on this? Who thinks we'll be able to run gradient descent? Maybe. Okay. Turns out we can't run gradient descent on this algorithm. The reason why is that we need that the v's are unit vectors. Okay, that means they're exactly linked one. This is a non-convex constraint. So we can't really apply gradient descent and get all these nice properties. Okay, so we can't do that either. So maybe the statistical reason is right. It turns out there will still be a nice algorithm for this. Okay, there's still a nice algorithm because we're using the sum of the squares, because the sum of the squares allows us to apply Pythagorean theorem. It's going to decompose into the individual vectors. We can solve for them one by one effectively. And there's going to be another algorithm, another really cool algorithm called the power method that we will apply in order to solve for this. And it will work because it's the sum of squared errors. Okay, and so we will see this as well. In fact, this algorithm will actually allow us to solve for a missing piece of how to do regression in closed form. It'll help us take the matrix inverse. Did we ever tell you how to take the matrix inverse yet? Okay, well, we have to solve that question too. Okay, so in order to actually solve regression in the closed form, we're going to need to solve this one as well. This will give us that algorithm also. Okay, so that's what we'll see over the next kind of, next week, I will give you kind of somewhat of a black box linear algebra answer for how to choose B. Then the next week, Monday, we will see actually what that algorithm is under the hood, the power method. And then on Wednesday after last week, there was this little assumption here that the subspace must contain the origin, and we will get rid of that on Wednesday next week. Okay, so that'll be the next 3 lectures. All right, stop here. Don't forget to finish your homework. Don't wait till the last minute on this one. It's a bit more programming.